we're taking an in-depth look at isosceles and equilateral triangles and really the impact that those sides of the triangle actually have on the angles of the triangles. If you look over here to the right, you'll notice that there's a triangle. The top part of this triangle is going to be called the vertex, and these two sides over here are going to be called the legs. These two congruent sides are going to be called the legs. The bottom is going to be called the base, and so these two angles here at the bottom, right here and right here, are going to be called the base angles. As we look at this, these are some of just the vocabulary words that we'll need to glean from this unit for us to come up with. So again, there's legs, there's vertex angle, base angles, and the base. As we look, here's a quick proof on the base angles theorem, which we're going to take a look at. I don't like some of the things that it starts off with, like starting off with the definitions here and there. There's some good stuff dealing with the midpoints and being able to use CP/CTC to prove that the angles are congruent when you're given the sides. But I don't think it really starts in a good place for us with where we are with proofs. These are the three theorems we're going to take a look at. Three really important things, maybe four. Is really the first thing is the base angles theorem. When we start off, the base angle theorem is probably the most important thing we're looking at today. Base angles theorem says basically if you have two sides of the triangle are congruent, the angles of the opposite are also congruent. In other words, that if you start off and you have a triangle and you have the two sides are going to be congruent, then you can show then that these two base angles will also be congruent. It's always going to be the sides opposite the angles. The converse to it, maybe the second most important thing we're looking at today, is really the converse, that if you start off and you have these two angles, then what you're going to have is you're going to be able to prove that the two sides are congruent. These two are easily mixed up. So the idea is with the base angles theorem, you're going to end with having the angles congruent. With the converse to the base angles congruent, you start with the base angles and end with having the sides congruent. Okay, so it's something to really kind of watch and to look into. Down here is kind of like a 3 and a 4 kind of things that we have already known in the past, we've talked about in the past. If a triangle is equilateral, then it's equiangular, and again, if a triangle is equiangular, then it's equilateral. Kind of a cool thing, I saw this in the book and said, hey, that's kind of a nice thing to point out. It says write as a biconditional, and the idea with this is that since we have an if, and then a then, and an if, and then a then, and they're basically converses of each other, then we could also go through and we could write this as a biconditional, saying that if, a triangle is equilateral if and only if it is equiangular. So it's kind of a nice thing to look at, kind of a nice thing for us to see. Let's get started with some of the work here. Some of these are really, really easy problems, so we'll try to focus on getting the right theorems and everything down. If you notice, we have all three of these angles are congruent. If all three angles are congruent, we could probably say that this angle is 60 degrees, this angle is 60 degrees, and this angle up here is also 60 degrees. Now that's going to be true for every equiangular triangle, is that all three angles are 60 degrees. Because of the corollary of the converse of the base angles theorem, we can then say that these three sides are congruent. If equiangular, then we have equilateral as well. Because that if this side's 6 over here, we know this side over here is also 6. Not tough to solve, but I guess the corollary to the converse of the base angles theorem is how you would prove that. Over here we have two sides congruent, so we know that these two base angles are congruent. The reason we know that is the base angles theorem. So if this side's 70, this side over here also has to be 70. Over here we have the two base angles congruent, so we can show that the two sides are congruent. This is actually the converse to the base angles theorem. So if this side's 18, this other side has to equal 18 as well. Hopefully this is pretty easy for you to see and understand. Let's move on. It's a little bit more complicated. This time we see that all three sides are 10. So by the corollary to the base angles theorem, we can say that all three sides are going to be 5x. Since all three are the same, we could also say that these are all 60 degrees, or that 5x is equal to 60 degrees. When we divide both sides by 5, we just get x equal 12. So that's how we'd go about and solve this problem. Over here we have two angles equal 60, so your brain probably thinks, well, what's that other angle got to be? Well, it also has to be 60. So if all three of these sides angles are the same, all three sides are going to be the same, we can simply say that 7 will equal 2x minus 3. When we add 3 to both sides, we'd have 10 equals 2x, or just that x equals 5. As we move over here, if we notice these two angles are the same, again we can say the two legs are the same. That's by the converse to the base angles theorem. So we can just say that 15 is equal to 4x plus 3. If we subtract 3 from both sides, we'd have 12 equals 4x, or just that x equals 3. And anytime you can always pause this and look over it again, listen to what I was having to say, and you can always get a little bit more in-depth knowledge that way. Over here, if we have the two angles congruent, we can say the two sides are congruent. That's by the converse to the base angles theorem. So we can simply say that 28 equals 9x minus 8. That would give us 36 equals 9x, or that x equals 4. Over here, there's a little bit different. We can't set 40 equal to 11x minus 18. What we can say is since these two sides are congruent, we can say these two angles are congruent. And one thing we can do then is we can say 11x minus 18 plus 11x minus 18, basically angle F up here, plus 40 degrees. All that has to be equal to 180 degrees. So that's by the triangle sum. So here's one angle, two angles, three angles adding up to 180 degrees. We can simplify that one step by having, this would be 22x, this would be minus 36 plus 40, so plus 4 equals 180. If we subtract 4 from both sides, we have 176 equals 22x. And let's see, if we divide both sides by 22, we'd have x equal to 8. Something else it might ask you to do is actually to substitute this in. You could say 8 times 11 is 88, minus this would give us 70 degrees here, 70 degrees here. We'd be able to figure out what these angles actually are. Over here, since we know that this is 13 and this is 13, we could say these two angles are equal to each other. Simply saying 7x plus 5 equals x plus 47. If we subtract x from both sides, we have 6x. If we subtract 5 from both sides, we have 42. Or simply that x equals 7. Next, this is a little bit more tricky. When you're sometimes given the vertex, there's kind of a different way that you could solve this. Because we know that this angle, the two base angles plus 98 have to equal 180, one thing we can do is we can sometimes take 180, subtract the 98, that would give us 102. This 102 is actually evenly distributed between these two angles. So that means if I divide that by 2, I know that each of those base angles has to be 51 degrees. That makes it a lot easier to solve for these since we do have different variables, an x and a y. I can say 51 equals 5x plus 6. When I subtract 6, I'd say this is 45 equals 5x, or that x equals 9. In a similar fashion, I can come over here and say y minus 9 equals 51. I can add 9 to both sides, and just x, or y, equals 60. So in this way, since this was an x over here and we have a y over here, we can't simply set our two expressions equal to each other, because then we have two different variables but only one equation. It doesn't, in similar fashion, it doesn't help us to add all three angles up in order to equal 180, because again we'd have one equation with two unknowns, and it doesn't really help us a whole lot. So we kind of have to watch that. We have to be a little bit creative in our approach, but I think we can make this happen. In number 15, since we know both these sides are congruent, we can say that both these angles are going to be congruent. So we can right away say that 53 plus 3x plus 8 is going to equal, 50, that didn't work out very well. 53 is going to equal 3x plus 8. When I subtract 8 from both sides, I'd have 45 equals 3x, or that x equals 15. Instead of plugging the 15 in, I know it's going to have to equal 53, so I can really just say 53 plus 53 plus 8y plus 10 has to equal 180 degrees. Again, I'm summing together the three angles in this triangle, and that to add up to get 180. If I add these together, this would be 106, 126 plus 8y, looking 180. When I subtract 126 from both sides, I would have 54 equaling 8y. I think I added this up wrong. This would actually be 116. That makes that 64, which turns out to be much nicer. And y just equals 8 in this case. Sorry, I misadded a little bit. I wrote the problem wrong and I misadded over here. So this is just going to be 116 when you add those together with the 10. Over here, very similar process because these two are congruent because of these the sides being congruent. We can just set those equal to each other. So 6y minus 5 is going to equal 10y minus 41. That would give us 4y equals, if I add 41 to both sides, let's see, that'd be 36, or that y equals 9. The tough part here is that I actually have to substitute the 9 back in here in order to get a quantity. So that'd be 9 times 10 is 90 minus 41. That makes this angle 49. And I know both angles have to be 49. Let me just check to make sure it works. So 6 times 9 is 54 minus 5. That does give me 49. I can then say 49 plus 49 plus 12x plus 22 has to equal 180 degrees, just using the triangle sum again. This would be 98 plus 2 is 100, so I have 120 plus 12x, that equals 180. When I subtract 180 from both sides, I have 60 equals 12x, or simply that x equals 5. So again, you're solving for two variables in these cases, and they can be a little bit more complicated. Sometimes you can't automatically set one angle equal to the other angle, but sometimes you can. So there's going to be a lot of variety in the problems that we have and what we're working with. Next, we'll look at this example here. You might just take a second and try these on your own. Why don't you pause it, try each of these three problems on your own, and we'll look at these in just a second. Welcome back. Hopefully you had a good opportunity trying those three problems on your own. Because these two sides are congruent, we can say that these two angles are congruent. This is by the base angles theorem. So we can say 3x minus 11 equals 2x plus 11. In other words, this is x equals, if I add 11 to both sides, that'd be 22. So I've quickly found my x variable. I'll substitute this back in. 2 times 22 is 44. 44 plus 11 gives me a total of 55 here. 3 times 22 is 66 minus 11 gives me 55 up here. That's nice that those two numbers do turn out to be the same. And I could say 55 plus 2y equals 180. This is 110 plus 2y equals 180. I'll subtract 110 from both sides, and I have 2y equals 70, or y equals 35. In the second problem, kind of an interesting idea, because this is 90 degrees, we know that these two angles must be complementary, or in other words, adding up to 90. And since these two sides are congruent, we know these two angles also have to be congruent. So congruent complementary angles, that means they both need to be 45 degrees. Since they're congruent and they're complementary, they need to both add up to 90 degrees and they're the same. It has to be 45 and 45. So I can simply say 3x equals 45, or x equals 15 in this case. I can also say y plus 7 equals 45, or y equals 38 in this case. Over here, a little bit more complicated. If I look on just the inside of the triangle to start off with, because these two sides are the same, I can say this angle over here is going to be x minus 2. I can say x minus 2 plus x minus 2 plus 4x plus 10. Those three angles have to equal 180 degrees. Let's see, I have 1, 2, I have 6 x's over here. I have 10 minus 2 is 8, minus 2 more is 6, so I'll say plus 6 equals 180. If I subtract 6 from both sides, I'm at 174, and 174 divided by 6 is 19, so x equals 19. If I substitute, I think it's 29. Okay, equals 29. If I say 29 minus 2, this is going to give me 27. So this small angle right in here is 27 degrees. Since these two are a linear pair, these two have to be supplementary. So I'm going to say 3y has to equal 180 minus 27 is what that would be. So 3y equals 153. When I divide both sides by 3, 15 divided by 3 is 5. 3 divided by 3 is 1. So y should equal 51. Okay. Again, the reason this worked out is because this is 27 here. 27 plus the 3y has to equal 180. These are two are supplementary. That might be an easier way to write this than whatever I wrote down there. Another way you could do this is you could say, since this is an exterior angle, you can use this idea of 1 plus 2 equals 3. The drawback on that is that you'd have to figure out what this actual angle is and what this angle is. This one's pretty easy. It's just 27. This is a little bit more complicated because 29 times 4 is kind of a weird number. Lastly, we're going to look at a proof really fast. This is a good proof, number 24. It kind of uses a lot of the ideas that we've been talking about. It starts off saying that BD bisects this angle at the top, CDA or ADC. So what that tells me is that these two angles are going to be the same. So this is a given piece of information, and what it does is, since it says bisects, notice it does say definition of angle bisector in the next line. I think that's just going to preclude that we say angle 1 is congruent to angle 2. So that gives us an angle. Our second piece of given information here is that segment DB is going to be perpendicular to segment AC. Because of this, we can actually draw this symbol. A lot of people think this symbol means 90 degrees. Well, it doesn't directly. Some people think it means, well, you have a right angle. But really what it means, what it really directly means, is that these two lines, or line segments in this case, are perpendicular. From perpendicular, we can conclude, hey, that's going to be a right angle. Whenever you see a right angle, you say, oh yeah, that's 90 degrees. A lot of times we jump from seeing this symbol right to 90 degrees. It's really kind of the transitive property. When you see this, you need to think those two lines are perpendicular, which means they're a right angle, which means they're 90 degrees. So we'll see in the proof, once we have this, we'll be able to say, hey, these two are right angles. Well, why is that? The reason they're right angles is because these are perpendicular lines. That's something that a lot of people kind of lose points on or don't really think about. And I think a lot of teachers kind of jump to this conclusion too. What does that box mean? Oh, that means it's 90 degrees. Well, that's kind of the easy way to say it, but really it means they're perpendicular, which means they're right angles, which means they're 90 degrees. The reason you could say that 3 and 4 are congruent is because they're a linear pair and they're right next to each other. What the way that's summed up is in the right angles congruence theorem. Actually says that if you have two right next to each other, if one's 90, the other one's going to be 90, they're also going to be congruent. We can also say that dB is congruent to itself by the reflexive property of congruence. At that point, we have a side over here, we have an angle here, and we have an angle up here. So we should have angle, side angle. We just have to prove these two triangles are congruent. A lot of different ways that you could name these angles. I'll just name them DA. That doesn't make sense. DAB is one triangle, and triangle DCB is another way we can name that other triangle. Once we know those two sides, we have these two triangles congruent. These two triangles are congruent. We're going to use CP/CTC in order to find something. The idea here is that when you go through and you try to figure out this is an isosceles triangle, what does isosceles really mean? Isosceles talks about the sides. Okay? When we classify triangles by their sides, you can either say that they are scalene, you can say they're isosceles, I'll abbreviate isosceles, or you can say that they're equilateral. Okay? So those are three ways of classifying triangles by their sides. So isosceles, though after today, we know that it also means angles, isosceles primarily means sides. So what I'm going to do is I'm going to say, hey, this side over here is equal to this side. So I'm going to say DC is congruent to segment DA. That's by CP/CTC. From there I can use the definition of isosceles triangles. Isosceles is a hard word to spell. A definition of isosceles triangles shows that that's an isosceles triangle. I have another quick proof here. Why don't you pause it? Why don't you try this? Really should be pretty simple. It uses the base angles theorem. It uses this triangle here. A little concept there, and this should probably be CP/CTC. Go back through, see if there's anything that you've missed throughout this lesson. There's a lot of algebra involved, really based on these three simple concepts, or four simple concepts here, the base angles theorem, the converse of the base angles theorem, and these two corollaries, which really help point out what we're working with today. Work on your assignments, and let me know if you have any questions. And if you have some extra time, go out there and realize that math is power. Have a great day, guys.